yeah, it's been a bit depressing the last few days. In the UK, we've got all this craziness going on, and every time I watch the news, I just want to, well, talk radio news, and even, well, I don't watch BBC News. I don't watch BBC, but or any of that stuff. I haven't watched that for years, but so I just wanted to have a little talk about distractions, really. I came across the channel William Enki, or was it James Enki? William Enki. I'll put a link in the description of this video, this live stream. And I was looking at his builds that he's been making. He's very enthusiastic, and he's very optimistic, I think is the word. The only thing I don't like is the swearing. I mean, occasionally gets a bit... Yeah, but I think it's a bit of an act, to be honest with you. I think he's putting a bit of an act on showmanship. But one of the problems with a lot of channels I've noticed is that they'll show you basically how to do it, to build what they're working on, but they don't fully understand what it is they're doing themselves, because it's usually based on somebody else's creation. Somebody else has invented it and they've copied it. That's the problem whenever you come across a design or a build that somebody else has created, and like Tesla. Apparently this technology is based on Tesla or something. So what happens is they don't fully understand it themselves, so they'll often describe certain aspects of the recreation. I suppose it's a recreation or reinventing the wheel, whatever. They'll often describe these aspects incorrectly. So basically, after looking at several of the videos from William Enki's channel, because I've got a lot of experience with radio frequencies and radio waves and transmissions, because we actually built a transmitter years ago as a hobby project. Whenever you're dealing with radio frequencies, RF as it's short for, you encounter unpredictable anomalies. The reason for that is RF it's a resonant frequency which interacts with the atmosphere and everything in the surrounding area that's conductive, magnetically conductive or inductive. Even your physical body, just human body, the touch, just being in that field will interact with that field, and it will create unusual phenomena. One of the most obvious phenomena and the most strongest overlooked phenomena is instrumentation malfunction. And basically what I'm saying here is that when people are measuring current and voltages, you have to have a situation of screening where the equipment is not being manipulated or interfered with by radio frequencies, because radio frequencies are very, very inhospitable, I think is one word. Very unpredictable is the other word, because the radio frequencies get into everything electrical, and if your equipment is not properly shielded, you can't trust anything that the instruments are saying. Now, from what I actually saw though, he was inputting something like 3 to 4 amps or so, and he was powering a light bulb at about 100 watts. Is that outside the realm of possibility as far as free energy goes? I'm doubtful. You know, I'm not convinced, I have to say. Because whereas radio frequency, you can, in a certain situation, produce power that's radiated. It's called radiant energy or radiated energy. Whereas you can emit energy of a high frequency and receive it on an antenna and convert it back into electrical power to drive a light bulb, all of that's perfectly feasible. But the question is, obviously you've got to have it in resonance to optimize the amount, because this another term of resonance is standard wave ratio, which is used commonly in radio frequency transmission. A standing wave ratio is when the waveform is in synchronization with the ground plane, so that you don't have oversaturation. If you have a high reflective, that's what it means basically. If you have a high reflective radiance of the signal that you're sending out, you get a high standing wave ratio, whereas the needle bangs across. I've got a swarm meter over here. Hang on, I'll just show you what I used to work on with CV radios. I used to fix them. There's my standing wave ratio meter, because I've got a CB which I don't actually use anymore. But that's my SWR meter right there. I've got a few bits of stuff in the cupboard still, but I used to make antennas as well, so I have a bit of an understanding. So whenever you're working with RF, ideally the equipment or the coils that are emitting radio frequencies have to be in a sealed box, because a shielded Faraday cage that's blocking of that specific frequency, because once you emit that radiation, that RF radio frequency, into the atmosphere, you no longer have a controlled environment. So what that means is that you can't trust your instrumentation, because most instruments, especially multimeters, are plastic. They're just, I mean, like my multimeter here, right? It's just a plastic box. If you take the circuitry, if you take the back off this meter, the circuit board inside it has not got any shielding on it. There's nothing there to stop the RF from going straight into the meter. So the meter itself could inherently pick up radio signals directly into the readout, to the circuit that drives the readout, and give you an erroneous reading, which says that it's 100 amps when it's not. The instrument has to work, a measurement device has to work where you have an isolated current travelling down the wires of the meter through a resistive network, and that is sampled by a comparator circuit, and then it's processed through all the circuitry to give you your digital readout. But RF can get into that meter without the leads even being attached. So normally what you'll find is, if you have your instrumentation and the leads are not connected to anything, and you spread them out, you move the wires apart, and you get a reading, you are actually picking up RF, you are picking up radio frequencies. So whenever you have a situation where your meter will read something and you're not connected to anything, you can guarantee it, and at 100%, that what you're actually receiving on your meter is radio frequency. The only way to isolate that, as I say, is for the source of the radio frequency, which could be a transmitter or a high-powered inductive coil near the meter, to be shielded in a Faraday cage, or have the meter and the equipment that you're measuring inside the Faraday cage. And most people, let's face it, it's not practical to put your oscilloscope and all of your meters in one Faraday cage, because you can't get to them. You can't turn the knobs without opening the Faraday cage up, unless you're in the Faraday cage with it, and it's just not practical. So well, the reason I'm talking about this is because there's such a lot of misunderstanding and misconception about this sort of thing. Now just give me a minute. Sorry about that, I had to grab this. I want to show you something. This is an antenna switch, and it's got coaxial antenna switch on it, and it's got 3 inputs, and this was used for switching between one antenna and another antenna. I used to use this years ago for the CB radio, when we used to switch from one antenna to another antenna, because you could just press your buttons in like this and you could switch whichever antenna you wanted on. Actually, I've just realised I could use this for something else. Anyway, if you look closer, you'll notice that this thing is in a metal box, and the reason for that is to stop the radio waves from escaping into the atmosphere and interfere with other equipment. Now, if you've never seen inside a TV tuner, this is a TV tuner, you'll notice that it's completely encased in a metal box. And the reason for that is to shield it from external interference and radio transmissions. I'm not sure if this is soldered on, or I think I can pop the lid off. But we're talking about very sensitive electronics. Yeah, there we go. So this is a tuner, for anyone that doesn't understand, and it's extremely sensitive to RF, which is why it has to have a metal shield on it to stop external interference from getting directly into the tuner, because you have your antenna socket. So I'm going over some basics here for those that don't know, because it occurred to me the other day that there's a lot of young people around now who probably don't have any experience with the older technologies, because everything, let's face it, now is digital now. It's all so compact inside your mobile phone, you can't even see it. I mean, basically this tuner is probably on a little tiny chip inside your phone, and it's so tiny you don't even know what it is, because everything's got so small now. But this is when things were a bit bigger. This was a TV tuner, and I kept it for, let's see if I can get this end off. The other side. Sometimes I solder on, you see. So need my screwdriver. They used to make these really well, actually, years ago. Let's see if I can get this off this end. Right, so now this is interesting. If you look in here, this tuner, you'll notice something quite interesting, right? Do you know what those? Do you know what these things are? Hang on a minute. Let me find my plastic screwdriver or something to point. Do you know what these little brass things are inside here? And they're in separate compartments. Those are antennas, or coils, inductive coils, and they're coupled by there's a small gap between each one. And the way it works is, let me just switch over to my other camera just a minute. It's easier, but the light's really bad here. Right, let me show you this under some decent light. Because a lot of younger people don't understand technology, I mean this kind of technology, because it's older technology and it's something you can see with your own naked eye without looking under a microscope. Right. Each one of these little brass or copper things is connected to a transistor. And what happens is it's tuned to a specific frequency, and one is transmitting a signal to the next coil, which is basically just, because this is UHF, right? This is UHF. So with UHF, you're dealing with very small nanometer sized waveforms. I mean, the waveforms are very small. So if you imagine that this was something in the long wave frequency, then this wouldn't be like this. It would be a giant wire that runs down your garden. Instead, it's not. It's UHF. So we've got a tiny little wire, effectively. So this will be driven by a transistor. It will send the signal to the next one, and then the next one will carry the signal, and each one of these compartments is completely shielded, look, so the signal can't get through. And the only place the signal can get through is usually through what they used to call feed-through capacitors, which was usually a small hole drilled in the side of the wall where you'd have a capacitor going through. But in this case, the frequency, let me see, I think it's this one, there's plastic here somewhere. In this case, there's a hole somewhere. I'm not sure if I can take that out. Yeah, there's a plastic thing here that separates that. That one's critical, so it's got to be a certain distance from this plate. So the signal basically bleeds through a small portion of this. These insulation, this steel wall is very thin, so a certain amount of signal can pass straight through, and it's coupled by some capacitors on the other side. These are I can't really see properly myself. There's some tiny little capacitors in there. See if I can get shine my torch. If I shine my laser, probably too bright. Yeah. So there's some little tiny capacitors down there, which are coupling capacitors. So anyway, I'm not going to go into too much technical stuff about this, but the point is, the point I'm making here is that with a UHF system like this, every single compartment had to be shielded from the next stage, right? Otherwise, what would happen if you didn't have any shielding? Well, I'll tell you what would happen is the final stage would feed back into the first stage, and you would get feedback, and basically it would become something like a super hyperdyne, but it would destroy the signal. Basically, a super high. I can't say the word nowadays. I'm getting too old. But basically, a super high dyne used to use a small portion of the output signal to feed back on the initial signal to boost it, to create gain on the signal. Well, is it heterodyne? I think it's heterodyne. I think. Anyway, but with this system, they had to isolate every stage to prevent any kind of bleed through coming back to the start, otherwise it would mess it all up. This is obviously that's where the antenna comes in, right? This part, that's where the antenna comes in. So this starts off as a weak signal. It gets boosted by a small microchip somewhere, or a transistor somewhere down there. My eyes are really bad. I think there's there should be a transistor down there somewhere. I can't even see it. Oh yeah, I think I can. Oh no. Damn it! My eyes are so terrible. Let me see if I can find it. Oh, the surface mount, they're on the other side, aren't they? Yeah, that's why. Yeah, the tiny little transistors are actually mounted on the back side. I'll take that one off again if I can. Hang on a sec. I'm going to break my nail in a minute. Ooh, right. Okay, so the transistors are actually on the back here. Those are the feedthrough capacitors. They're actually in the board, in the circuit board. That's how sensitive this is. So, right. Let me just turn this over a minute. So that's the input side here, right? And each stage, as you know, it's shielded on this side, right? If you look where that wall is about here, right? Follow where that wall is. The wall is about there, right? If you look on the other side, you'll see that where that wall is, what do we have here? Right there is a feed-through capacitor. It's a disc capacitor without any legs. And that's a disc capacitor without any legs. It's mounted between each section. So this is what carries a signal through to the next stage and so on, right? So these are all separate stages, and they're very tiny. And that's how sensitive. Oh, that's blob of solder. That's it. Right. There's a disc capacitor. Let's try my laser there. And what's the next one? They're all over the place actually. There's one there, and there, that one, and that one. Very tiny, right? So this, you could tune these. You could mess these up, right? You could mess these UHF tuners up just by putting too much solder on a pin, right? If you put a large blob of solder on one of these pins, you could knock the frequency and the tuning out completely. So when they used to make these, they had to measure exactly how much solder they put on all of these pins, because that affected the inductance of the circuit. That's how sensitive these things used to be. Well, but we just don't use them these days. Now it's all microwaves and everything's basically so condensed you can't even see it anymore. Everything's just got so small. So anyway, I was having a rant about it, and I thought I'd just share some of my knowledge before I croak it or drop dead or whatever, because I mean, let's face it, everyone I've got that backwards, haven't I? Yeah. Oh well, I'll put that right in a minute. So anyway, I thought you might be interested in that. So okay, so what else was there? I'm gonna have to put that back together in a minute. So the other thing is, I did this boating thing because I was testing it out, because I wanted to see if it would work, and I did actually try to boat on my own pole, but it doesn't seem to work very well. It doesn't work really unless I'm on my other account, but it's just I wanted to make sure it worked for everybody. The reason for doing that was because at some point when I get when I'm working on some of my designs, it would be nice to be able to ask my viewers what they think about a specific design. Or so what I'm working on is this thing at the moment. I drew a rough outline of it. This is a cross section. So this little box in the middle is basically the coil, and then we have these little legs that come out. That's the core material that comes out the coil and comes to the front. My idea is that we could use some kind of flux trap, so that as the rotor is coming in, the field hits the side of this shielding and it goes around both sides, the back of the coil and the front of the coil. So as it's entering, the field would basically pivot. So this is like an elongated toroidal effect. The idea was that as the magnet's coming in, the field won't be directly opposite the coil until it gets past this point, and then the field will travel through and energize the coil. But inside of each one of these, I'm going to be inserting some magnets to act as my flux reversal or anti-lens reversal effect. So that's what I'm working on at the moment. I had this premonition thing, the situation. I was drawing these little hooks, right? And this is what based on that, because I thought, well, maybe that's not literal. Maybe it's just to give me an idea. What I need to do is to fold the field around it, and this is where this comes from. So I did a bit of thinking about that, and so I thought, well, maybe that's what it's trying to tell me, is I need to... Where's the light gone? Funny. So maybe I need to do something more like that. But I've got to model it in SketchUp, and I'm still thinking about it though, because I want to make sure I get it right, because I don't want to waste my time and money and all that, because I don't have much money, and you know. So anyway, so that's what I'm thinking about at the moment, this general idea. This thing here, it would basically be a piece of plastic with some electric foil around, all the way around it, a bit similar to some of those things I made for a magnet motor I was playing around with a while back, but much smaller than that. Anyway, that's currently what I'm thinking about. I don't want to rush into it, because I might change the size of it a little bit, because I'm going to see if I can use an existing some existing coils I've already got, to try to save money on copper wire and all that, because I have got some coils I could probably use, which, I mean, as well as these are a bit long though. These are a little bit long really. I want some short fat coils. I have got some of those lying around, which I use for the Alnico magnets, Alnico switching transformer, which I built. So I could use those short fat ones, and because I want to condense it a little bit, you see, because it's an experimental setup, so it's just a one-off to test the idea out to see if it actually works, and I could use it in either generator then. So yeah, that's what I'm thinking about at the moment, but I wanted to cover that stuff about the RF and all that, because there's such a lot of, I mean, it annoys me, because I watch a video and it's frustrating when you see somebody saying, oh, what's going on here, what the heck, you know, what's going on here, sort of, you know. I know what's going on there, it's RF. I mean, RF does weird shit. So I'll put this right around. Let me just try to put this back together. That, oh yeah, that goes on that side because it's got adjustable holes in it. Yeah. So I just want to put this back together because it's kind of a collector's item, this tuner now. You don't see them around much except in TVs. Yeah, put that back together so it keeps all the crap out. So yeah, I could use this I could use this to switch power actually. I had sockets plugged into yeah, I probably won't. Yeah, I just used to have this up on my flat wall in the 1980s, and it's got paint all over it. I'll have to clean that up sometime, I suppose. Anyway, thanks for watching. I'll schedule this to go live tonight, I think. It's 20 past... It's 20... Oh, actually, what is it? That my clock's fast over there. Nearly 9:15 in the morning, so... Yeah. I'll set it to go live tonight. Alright, thanks for watching.